Hi. Okay, so we are doing problem P1C.16. The equation of state of a certain gas is given by P as RT over Vm plus A plus BT over Vm squared. Find dVm dt or partial V partial T at constant pressure. In class, I talked you through one way to do it. This is the longer way. I thought a video would be better so you can kind of follow along. Okay, we have P of VMT, but we want V as a function of T and P, so we can just take the derivative. So this is where it gets a little tricky because we have the partial V. So if you had the function of V, you could just take the partial derivative and call it a day. Well, how do we do that? Well, we can introduce the exact differential of the volume. So we know that the volume exists as a function of T and P, which means the total differential of the volume with respect to T and P, oops, so it's just the total differential, is equal to the partial derivative of V with respect to T at constant P multiplied by the actual change of temperature that occurs plus the partial derivative of V with respect to P at constant T conditions multiplied by the actual change in the pressure. Okay, so the goal is here. Goal. So by constraint, so here's the fun thing. By specifically constraining the system by holding P and T constant, we can set, or by setting, and actually I'm not going to say it's by holding them constant, I am going to set equal to 0. Okay, and so by setting this equal to 0, what that means is in my function box, where this is my volume, and then my T and my P are my conditions that I can turn my parameters and I can move this needle. What happens is to set this equal to 0, I can turn both P and T such that if I turn P, the needle will move. If I turn T, the needle will move. But I'm going to turn them in a perfect way such that that needle doesn't move, and each one changing cancels out the other one's change or effect on the needle. So, hence, the total V, change in V, is 0. So that's really what I'm setting up. I'm hoping that you'll be able to make these assumptions as we progress through some more challenging problems. Okay, by doing that, what I now do is I introduce that this becomes dV dt at constant P dt equals negative partial V partial P at constant T dP. Okay, well now what I can do is I'm going to say, well, I want to take, how does this change with a function of T of both sides? So I'm going to say, all right, well, how does each side change with respect to T? Well, that's pretty cool. That means that this becomes partial V partial T, there should be an M there, with P held constant, dt dt is now equal to negative partial V partial P, my apologies, that should be a T, total P total T. Okay, cool. So then what I can do is I can say, well, this is going to cancel. And now the requirement from before that got me to this state was that this was constant. And because I made this, I imposed this condition, that means that if I got to here, that's only under the condition that dV is constant. Well, here I've got P is constant. Here I've got T is constant, but right here, that means that V sub M is constant. Well, that's pretty awesome. So I'm going to pause there, and now I'm going to erase. Okay, so this is what I have now. It's a simplified version. So I've got dV partial V partial T at constant P is equal to negative partial V partial P at constant T, partial P partial T at constant V. Okay, now what I can do is I know that I have P is equal to, what was my original function? RT over VM plus A plus BT over VM squared. Well, I have this, so I can actually easily take dP dV at constant t. That would be really easy for me to take. Oh, that's really cool. Look, I actually have this, but it's the inverse of it. So one of Euler's relations, if you look at Math Kit, I think, or Math Toolkit, I think it's number 5. I should look that up. Math Toolkits 9 and 10. Number 9 is on page 44, and number 10 is page 105. Okay, so because I have this function right here, so what I can do is I can say that d partial p partial v at constant t to the -1 is the same as this. Actually, it would be a negative. So I'm inverting it. So I'm basically saying that x over y is equal to y over x to the -1 power. Cool? So by doing that, I can say, well, I know then what partial p partial v at constant t is, because that's equal to minus RT over VM squared plus A plus BT divided by VM cubed times a -2. Make sure you can do that derivative, and you see how I get from here to here. Again, these are skills you have to have in this class. That you go team, but we're working on it. So again, you'll have a lot of practice. Okay, so if I simplify this, I'm going to then get this equals minus RT V sub m minus 2A plus BT all over VM cubed. Okay, the other thing I can do is, well, I know dP dt. So what that is, oh, and by the way, remember, this is dP dV at constant t, not negative dP dV constant t -1. So you'll have to take all of this, incorporate the negative sign, and invert it when you plug it back in here. Okay, I'm not going to do all the work for you. Next, we've got, let's see, this part, dP dt at constant v is just, oops. Okay, so now we've got dP dt at constant v is just r over vm plus b over vm squared. Simplifying that, r vm plus b over vm squared. Cool? Okay, so you would plug this into here. You would plug the inverse of this with a negative sign into here, algebraically manipulate, and then you should get, after doing that, dV dt at constant p equals r vm plus b divided by 2 pvm minus rt. Awesome? Okay, I highly encourage you to go through the steps that I skipped. This will help you through this class. After chapter 2, you should be able to do these problems. But through chapter 2, we're going to be building and building these skills. This is the time to build these skills with this particular problem. So do this both ways. Go back and try it again with the way that I showed you in class, and then try and do this and fill in the gaps that I skipped. Go team. Bye.